All right, so we're moving along in chapter 8. And to remind us of what we were doing last time, right? We had learned how to do a hypothesis test of a single mean using two different methods, a critical value method and a p-value method. And in the lecture notes here, I have in section 8.2 this kind of little side-by-side comparison, because I think sometimes that's really helpful. For the critical value method, I just wrote down like three kind of brief steps. Right? You use alpha to find z or t values, and then you shade in the rejection region. So this is an example here of a two-tailed test where we shaded in both tails. And then you calculate the test statistic and you see if the test statistic lies in the rejection region. And if so, we reject the null hypothesis. Okay, so, we use this button and Alex in order to find the critical values. And then for the p-value method, there's that same kind of basic idea where we write a null hypothesis, an alternative hypothesis, and take a sample and so on. And now you use a test statistic, either Z or T, to find P, right? To find that P value. And then if P is less than or equal to alpha, then you reject the null hypothesis. So for the p-value method, we're going to use this button in Alex because P is the area, right? It's the area that's being shaded in the tails based on the test statistic. Okay, so for the critical value method, you're using that Z or T button. And for the p-value method, you're using this, P of Z or P of T button. Okay. So let's go back to the homework. All right. So I just wanted to pull up one of these intro topics, each using the critical value method and the p-value method, just to kind of remind us how to do these. Okay, so over the years, the main customer satisfaction rating at a local restaurant has been 92. It was recently remodeled, and now management claims it's not equal to 92. So remember, the null hypothesis is always the equal statement. The alternative is that it's not equal to. So this is a two-tailed test. And there was a sample taken of 68 customers. We got the sample mean. And then we also know the population standard deviation. Okay, so you're asked to do a hypothesis test at the 5% level of significance. Since this is a two-tailed test and alpha is 5%, you're going to have 2.5% in each tail. So you've got 95% and you've got 2.5% in each tail. Okay, so this Z gives you the 0.025 in the right tail, as it says here. Okay. So again, this is a two-tailed test. We want to enter the critical values. So we're going to do Z 0.025. So you get positive 1.960 and negative 1.960 because a Z distribution is symmetric. So you've got the two tails forming the rejection region. And then we calculate the test statistic and see if it lies in the rejection region. So this is how we calculate it. So the mean, the sample mean, the sample mean is 87.4. Minus mu is 92. Over the population standard deviation sigma, which is 14.3, over the square root of the sample size, which is 68. Okay. So this is how we calculate the test statistic. So we get negative 2.6, oops, 2, 2.653. Okay. And that does lie in the rejection region. So the null hypothesis is rejected. All right. And then for the p-value, let's see, for certain knee surgery, a mean recovery time of 9 weeks is typical. With the new style of physical therapy, a researcher claims that it's less than 9. So the null hypothesis is that mu equals 9, and the claim is that it's less than 9. So that is the alternative hypothesis. Now we're doing a z-test and finding the p-value, which is the area separated by that test statistic. Okay, so this is a one-tailed test. And now we calculate that test statistic. Okay, so the sample mean was 8.9 minus mu of 9 over sigma. That's the population standard deviation, which is known to be 0.9 over the square root of the sample size, which is 84. Okay. So that's the test statistic. To 3 places. And now we're going to shade the area represented by the p-value So this now is the area to the left of that z-score. Okay. This button gives us the area to the left of the z-score. And notice this is a left-tailed test. So the area to 3 decimal places is 0.154. Now alpha is 0.05. This is not less than 0.05. So since the p-value is greater than the level of significance, the null hypothesis is not rejected. Okay. All right. According to a report done by S&J Power, the mean lifetime of light bulbs at manufacturers is 48 months. A researcher consumer advocate group tests this. And for the bulbs in the sample, we have the mean, we know the population standard deviation, and can we conclude at the 10% level of significance that the mean differs from 48 months? So the mean equals 48. And then we want to know whether or not it does not equal 48. That's what we're going to test. Okay. We have a normally distributed property, and we know the population standard deviation. So this is going to be a z-test. Okay, find the value of the test statistic. Try to get this in. So the value of the test statistic, it's x bar minus mu over sigma divided by the square root of n. So we've got a sample mean of 50 minus mu is 48 over the standard deviation of 6. And we have a sample of 19. To 3 decimals, 1.453. Now, this is a two-tailed test. Okay. So we have 1.453 and negative 1.453. And so you have half p here and half p here. So this button gives us the area to the left of a z value. So since this left tail gives me half of p, I could take twice what's in this tail. Okay. So 0.146. And alpha is 10%. This is greater than alpha. So we don't reject the null hypothesis. Okay. Let's just see another one. Mean SAT score, standard deviation, special prep course claims that the SAT score is greater than 599. So an independent researcher tests this by taking a sample of 80 students and the mean in the sample. Can they claim at the 5% level of significance that the mean is greater than 599? Okay, so that's a one-tailed test. Um, the null is that it is equal to 599, and the alternative is that it's greater. Okay, you have a big sample size, and we know sigma, so you can use Z. And then you calculate that test statistic. This is a right-tailed test. So you want this area to the right. So you have to subtract the area from the left to the left from 1. Okay. The area to the left plus the area to the right equals 1. So to get the area on the right, you subtract that from 1. That's the area from the left. Okay. And that's almost, over 9%. It's greater than 5%. So no, we don't have enough evidence to reject. Okay. All right. And then we do the same basic idea for problems where we're going to use a t-test. So all the same basic idea. We don't know sigma, so we use the sample standard deviation. And then we have to know what the degrees of freedom are, which is 1 less than the sample size. All right, so a sports science group claims that due to improved training methods, professional cyclists burn a mean of less than 6,500 calories during the annual Monaco endurance race. This would be an improvement of the previously accepted value of 6,500 calories. Okay. And so they're claiming, and you can see here in the question, complete the parts. Is there enough evidence at the 10% level of significance to support that mu, the mean number of calories they burn, is less than 6,500? Okay. So again, that's a one-tailed test. We have a 10% level of significance. We have all of this info. So N is 17. The sample mean is 6394. The sample standard deviation It's 175. Right? And of course, mu is 6,500. And alpha is 10%. Okay, so since n is 17, the degrees of freedom, it's one less than that. Okay. Notice when you put in the degrees of freedom, the graph for the distribution is drawn. Right? This is a one-tailed test. And now it's alpha of 10%. So we want that area in the left tail. We can do the opposite of t of 0.10. Right? That gives us the area in the right tail, but we want the left tail. Right? So you could put a negative in front. There's 16 degrees of freedom. Okay. Negative 1.337. Now we're going to calculate this test statistic. I don't know if it's easier to write it all out or just look and put it in the calculator. Right, you've got X bar minus mu over S over the square root of 17. Okay. So this gives us the test statistic. And we can see the test statistic lies in that rejection region. So since it lies in the rejection region, the null hypothesis is rejected. So again, same exact idea. We're just using, this formula here for the t test statistic, which uses S instead of sigma. We don't have sigma. Okay. And then the same idea using the p-value method. Tardigrades or water bears are a type of micro animal famous for their resilience. In examining the effects of radiation on organisms, an expert claimed that the amount of gamma radiation needed to sterilize a colony of tardigrades no longer has a mean of 800 grays. Right? And sometimes I just jump and look at the question here. Is there enough evidence at the 10% level to support the claim that the mean is not equal to 800 grays? So the null is that mu equals 800, and the alternative is that it does not. And so let's write down some of the info here. So we have mu is 800. A study was done on a sample of 15. That's a small sample size. And the sample mean was 820. Sample standard deviation is 42. Assume we have a normal distribution. We don't know sigma. So we're going to use a t-test. And then we have alpha at 10%. So enter the degrees of freedom. The degrees of freedom, it's always one less than n. And again, as you enter that, the sampling distribution graph gets drawn. And since we have a does not equal to, this is a two-tailed test. And then we want to calculate the test statistic. So we have x bar minus mu over s divided by the square root of n, which is 15. It was 42, right? Just making sure I can read my handwriting. Okay. Okay. So this is the t test statistic. So that's 1.844. Okay, since it's a two-tailed test, notice they also put the opposite, right? Negative 1.844. We can shade that region in, and now we want to get the area. So look at the button in Alex. This gives us the area to the right of a t-value, okay? So you want to go to the right of the positive 1.844 with 14 degrees of freedom, and then take twice that, right? Because you've got half in the right tail, half in the left tail. Uh, 0.86. Okay, and that is less than alpha. So the null hypothesis is rejected. Okay. It's all the same idea. All right. A coin-operated drink machine was designed to discharge a mean of 9 fluid ounces of coffee. In a test, we've got all of that. Is there enough evidence at the 5% level to conclude that mu is different than 9? So the null is that it equals 9. The alternative is it does not equal 9. We have a very small sample size of 16. We have a normal distribution, and we are not given a population standard deviation. So this is going to be a t-test. Okay. So I could write down all the same stuff. We got mu is 9. We have a sample size of 16. So the degrees of freedom are 15. The sample mean is 8.96. Sample standard deviation 0.13. And alpha is 0.05. Okay, so we have a t-test with 15 degrees of freedom. We're going to calculate the test statistic. Using that formula. So we just plug in the numbers. So we have 8.96 minus 9 over S divided by the square root of N. Okay. So this is our test statistic. Negative 1.231. Okay, so this is a two-tailed test. We have a test statistic here of negative 1.231. But in a two-tailed test, I have to also cut off the tail with positive 1.231. Right? So P is that total area. This is half P. This is half P. So I want to take twice the area. Notice this is to the right. So I want twice the area in the right tail. "15 degrees of freedom," and I'll take twice that. Okay. .237. And that's greater than alpha. So no. Okay. So no, we cannot reject the null hypothesis in favor of that alternative. Okay. So again, all the same basic idea that we've been doing here. All right. So next up in 8.3 is hypothesis testing of a single proportion. Okay, much like how we saw designing or constructing a confidence interval for a proportion. And so we're going to be doing the same exact idea. You know, we have to be careful that n times p and n times 1 minus p are both greater than or equal to 10 before we can use the z-test. So we just need, you know, kind of large enough numbers in both those categories. And then the formula for the test statistic is different. Now notice on the top, we have p hat, we say minus p. P hat is the sample proportion. So see, this is similar to the sample mean minus the population mean that we've been looking at, right? Instead of the sample mean minus the sample minus the population mean. We have the sample proportion minus the population proportion. And then instead of z over the square root of n, we have this. So the sigma is kind of like the square root of p times 1 minus p. Okay. But again, we're doing the same kind of basic idea. So first we have a question to determine the null and alternative hypotheses. Past records from a local hospital stated the proportion of full-term babies born in the hospital who weigh less than 7 pounds is 48%. Suppose we have a strong reason to believe that the proportion is greater than 48%, and we want to do a hypothesis test. State the null hypothesis and the alternative hypothesis. So the null is that the population proportion equals 48%. So that's P, not P hat. P hat is the sample proportion. And I don't know, it might help to just think of, again, X bar is the sample mean. So it's like when there's something on top, it's kind of modifying it to mean it's for the sample. But so the null and alternative have to be about the population. So it's just P. And then we have to use the P on the palette. We can't type using the letter P. So here, the proportion of residents in a community who recycle has traditionally been 67%. A policymaker claims it's less than that now. Okay, so P equals 0.67, and now P is less than that is the claim. Okay. So again, you have to use this P on the palette here. Okay, on a nearby college, there's a school-sponsored website that matches people looking for roommates according to school's reports. 36% will find a match their first time using the site. A writer for the school newspaper tests this claim by taking a sample, blah, blah. So do the test at the 10% level of significance to see if you can reject the claim that the proportion equals 36%. Okay, so this first one will look, it's the same basic idea. But so the null hypothesis is that the population proportion equals 36%. And then the newspaper is, wants to test and see whether or not it is or not. All right, and then we have to do n times p and n times 1 minus p, and just make sure that they're both greater than 10. Okay, so the sample had 160 students. So you have 36% of 160, and then you have 64% of 160. Right? I mean, this is over a third. Clearly, it's going to be bigger than 10. And then 64%, I mean, that's over half. So clearly it's over 80, it's over 10, right? Again, we want to make sure these numbers are both big enough. Okay. And then this is a two-tailed test because we're testing to see if it doesn't equal that 36%. For alpha of 10%, you have 5% in each tail. And then you calculate the test statistic using that formula. Right. So you've got the two critical values, and then you see if the test statistic lies in the rejection region. Here it does, so you can reject the null hypothesis. Okay. All right. According to a report done last year by the dental industry, 81% of dentists would recommend Starry White's toothpaste. After some recent negative publicity, the sales team suspects the proportion is lower. Okay, so you're going to do a test to see whether or not you can conclude that proportion is less than 81%. So the null is that it equals 81%, and the alternative is that it's less than 81%. All right, so you've got P. You're doing a sample of 140 dentists. 110 of the 140 would recommend. So that is the sample proportion. And then you've got alpha of 10%. Okay. And so N times P N is 140 times P is 81%. Again, I mean, clearly it's bigger than 10. I mean, in practice, you would kind of eyeball that. I guess if you were writing a paper, you would, probably write it out and justify. And then N, which is 140 times 1 minus P. So instead of 81%, that's 19%. Okay, so still obviously bigger. Alpha is 10%. You have a one-tailed test, right? So that's why they're giving you that Z of 10%. And here's how you calculate the test statistic. All right, so this is a left-tailed test. So you want to get, the opposite of the critical value that's on the right. So it's negative 1.282. Right? The positive, like it says here, this is positive Z. That cuts off 10% in the right tail, but we want the critical value that cuts off 10% in the left tail. Okay. And then you can calculate this test statistic. So on the top, you've got the sample proportion minus the population proportion over the square root of P times 1 minus P over N. Okay. So this is the test statistic, negative 0.732, which does not lie in that rejection region. So since it doesn't lie in the rejection region, the null hypothesis is not rejected. And then the p-value method. The magazine TechWorks reported that 87% of software engineers rate the company they work for as a great place to work. As a veteran headhunter, you claim the percentage is not correct. So you do this survey, do a hypothesis test, see if there's enough evidence at the 10% level to support the claim that the proportion is not 87%. Okay, so the null is that it is, and the alternative is that it is not. Okay, so this is a two-tailed test. So you have a random sample of 210. The sample proportion, it's 188 out of the 210. You could get a decimal for that too, but I just leave it. And alpha is 10%. Okay. So find n times p. So 210 times 0.87. And then n times 1 minus p. Oops. So that's 13%. Both of which are greater than 10. All right, so we're doing a two-tailed test. We're going to calculate that test statistic. So you do 188 over 210 minus p over the square root of p times 1 minus p over n. Okay, and this gives us our test statistic. .088. Okay, it's a two-tailed test. So notice we have 1.088 and then the opposite. Okay. So we have a half of the area in each tail. This gives us the amount in the left tail because it's to the left of. So I'm going to put the negative z number in here. And then I'm going to take twice that. Okay, and that is way bigger than 10%. So since it's greater than alpha, the null hypothesis is not rejected. Okay. All right, the proportion of residents in a community who recycle has traditionally been 70%. Policymaker claims it's now less than that since one of the recycling centers has been relocated. So a test is done. Is there enough evidence to support the claim that it's less than that now? So you want P equals 0.70, and then P is less than 0.70. Okay. And so kind of want to see how Alex explains this. These are all going to be z-tests as long as the n times p and the n times 1 minus p works. And then we're going to calculate that z-test statistic. Hmm. Okay. Here's our formula for the test statistic. And so we know that P is 70. And then P hat, it's 154 out of 240. So N is 240. And of course, alpha is 1%. Okay. So we've got 154 over 240 minus 0.7 over the square root of P times 1 minus P over N, which is 240. Negative 1.972. So that's our test statistic. Right, so we want this area. So that's the area to the left of negative 1.972. To three places, 0.024. Small as it is, it's bigger than 1%. So the answer is no. We don't reject the null hypothesis. Okay. All right, so Let's stop here. And next time, we're going to look at the last section in chapter 8, hypothesis testing of a single variance or standard deviation.